Hi all, welcome back to System Verilog sessions. In this video, I'm going to discuss about transition bins. So what is transition? Transition means changing from one state to another state. So similarly in transition bins, if the bin is changing from one value to another value, then that is called as a transition bins. Okay, so transition bins are not, it's not a keyword. It's just a how we write the bins. Okay, that is called as a transition bins. So in coverage, each coverage point includes a set of bins associated with its sampled values or its value transitions. In coverage, each coverage point includes a set of bins which is associated with its sampled values or its value transitions. And the bins associated with value sets are referred to as state bins, while the bins associated with value transitions are referred to as transition bins. We can categorize the bins as state bins and transition bins. So what is this state and transition bins? State bins means it is used to track the individual values of variable. It counts how often a variable takes a specific value. Okay, how many times the specific value has occurred for the variable. So, but in what is transition bins? Transition bins are used to track how a variable changes from one value to another value. And it will not count the individual value of a variable. It counts the specific sequences of value changes. Okay, so here it will not count the individual value. It will count the specific sequences of value changes. For example, in state bins, we will check whether A has occurred or not, whether B has occurred or not, or how many times A has occurred, how many times B has occurred. But in transition bins, we will track whether the value is changing from A to B or not. So here we will check the sequence of value changes, right? If the value is changing from A to B, then it will be counted. Okay. So state bins are used to track the individual values of a variable. Transition bins are used to track the sequences of value changes. Okay. So these are all the differences between state bins and transition bins. And transition bins are used to track sequences of state or value changes in a variable over a time. Sequence is nothing but it's related to time, right? So transition bins are used to track the sequences of state or value changes in a variable over a time. Okay. And this is used to represent the transition of a variable. This operator is used to represent the transition of a variable. Okay, A and this operator B. So then it is called as a transition bins. So whether the value is changing from A to B or not. By using this operator, we will represent the transition bin. And transitions can be covered for the below legal cover point transitions. We will see what are the legal cover point transitions. Okay, the first one is single value transitions, sequence of transitions, set of transitions, consecutive repetition, range of repetition, go to repetition, non-consecutive repetition. So we will see each one by one. Okay, the first one is single value transitions. What is single value transition? As the name suggests, the bin will be changing from one value to another value. Okay, here if you see value 1 and value 2, between we are using the operator. Okay, so the bin will be changing from one value to another value. This is the syntax to write the single value transitions. Okay, cp1 cover point data bins b1 equals to 2 and 5. So the bin will be changing from 2 to 5, 2 to 10, 3 to 8. So this is the single value transitions. And next one is sequence of transitions. So here we will be writing the sequence of values, value 1 to 2, 2 to 3, 3 to 4. So 4 values, right? So this is how to write the sequences of transitions, 2 to 5, 5 to 6, 3 to 8, 8 to 9, 9 to 10. This is the sequences of values. And the third one is set of transitions. Here we will be having two sets, transition set 1 and transition set 2. Okay, so this is the example for set of transitions 2, 3 and the operator 4, 5. So here there are total 4 possible combinations of transition. If you see here, this is equivalent to this one, 2 to 4, 2 to 5, 3 to 4, 3 to 5. Okay, 2 to 4, 2 to 5, 3 to 4, 3 to 5. Okay, total 4 possible transitions are there. Since I'm using vector bins, here 4 bins will be created. Okay, if you write the scalar bin, then only one bin will be created. But since I'm using the vector bins here, it will generate 4 bins. Okay, so this is the example for set of transitions. So the fourth one is consecutive repetition. In transition bins, consecutive repetition means the sequence of value changes will be in the consecutive order. Okay, you know what is repetition. Repetition means the same value will be repeated multiple times. And when it is repeating, there should be no other value in between them. Okay, that is nothing but a consecutive repetition, and it will be represented by using the star operator. If you see here, transition value, star repeat value. So here 4 star 3. 3 means 4 is repeating 3 times. Okay, this is a repetition value. 4 has to repeat 3 times, and when it is repeating, there should be no other sampled values between this transition. Okay, that is nothing but a consecutive repetition. And here I'm using the vector bins, so there is only one transition sequence, right? So only one bin will be created. Okay, and the next one is range of repetition. So here we are giving the single value. 4 is repeating for 3 times, but here we can give the range of repetition value. Okay, so 4 star 2 down to 4, that means 4 can be repeated for 2 times, 4 can be repeated for 3 times, 4 can be repeated for 4 times. There are total 3 possible transitions here, and this is a single bin, right? And here you can see 4 can be repeated for 2 times, 3 times, 4 times. There are 3 possible transitions, and we are using the scalar bin, so only one bin will be created. And here we are using the vector bins, and there are 3 possible transitions: 2, 4, 2, 3, 4. So 2, 3, 4. Total 3 bin will be created. Okay, so this is the range of repetition, and here we cannot give the dollar while representing the range. Okay, that is not allowed here. You cannot use the dollar, so you can just give the value, specific values. So the sixth one is non-consecutive repetition. So non-consecutive repetition can be represented by using the assignment operator. How we are using the star operator to represent the consecutive repetition. Similarly, we will use the assignment operator here. Okay, and that is a non-consecutive repetition. And non-consecutive order means while repeating the values, there can be occurrence of other values. Okay, there can be other sampled values in between the repetition. If you see in the consecutive, there should not be other value between the repetition, right? So that should be the consecutive order one by one. But in the non-consecutive repetition, there can be other sampled values. You see here 2, after that 5, and I'm repeating 5 3 times in the non-consecutive order by using this operator, and 7. So this is equivalent to this one. 2, after 2 any value can come, then 5 has to repeat 3 times in the non-consecutive order. See 5, this dots are nothing but any value it can take. Okay, after 5 3 can come, 4 can come, any value can come, again 5, and again any value can come, again 5. This is the important thing in the non-consecutive repetition and goto repetition. Here you just focus here. Okay, so after 5, the last repetition value, any value can come, then the last transition value should come. Okay, here so 5, how many times 5 has repeated? 1 2 3, 3 times it has repeated. So this is the equivalent form of this one. And if in the goto repetition, this is also non-consecutive repetition only, but the thing is, here's the same example I have taken. Okay, after 2 any value can come, 5 has to repeat for 3 times. This is the operator used to represent the goto repetition. Goto repetition is nothing but a non-consecutive repetition only. But if you see, after the last repetition value, this 7 is there, the transition value 7, that has to come immediately. Okay, after the last repeated value, whatever the transition value is there, that has to come immediately. Here if you see, 7 is there. After the 5, any value can come here. Okay, 7 doesn't have to come immediately. Okay, here any value can come, but here in the goto repetition, after the last sequence, if any other values are mentioned, then that value has to come immediately. Okay, after the last repetition. So this is the only one difference between goto repetition and non-consecutive repetition. Okay, so after the last occurrence of a value, the next value should come immediately. Okay, there should be no other sampled values between the last transition value and the this one, the last occurrence of a repeated value. But here any sampled value can come between the last occurrence of the value and the last transition value. Okay, so this is the only difference. If you remember this one, it will be easy, and it will be same in assertions also. Okay, in assertions also, this consecutive and the non-consecutive goto repetition will come. That time also the concept is same. Okay, so goto and non-consecutive is very important. You need to understand this difference. Okay, after 5 any value can come, and then 7 can come. So here after the last occurrence of a value, the next transition value should come immediately. This immediately word is very important. Okay, so this is the one difference between goto repetition and non-consecutive repetition. And multiple transition bins cannot be used to specify a sequence of undetermined number of transitions. So that means here I am using scalar bins, right? B1 like this. Here I cannot use the vector bins. Okay, multiple transition bins cannot be used to specify a sequence of undetermined number of transitions, or transition sequence of unbounded or undetermined varying length cannot be used with the multiple bin construct. Multiple bins means vector bins. So here I cannot use the vector bins for the non-consecutive repetition transition bin or goto repetition transition bins. Only scalar bins are possible here. Okay, because the repetition, any after one value, here after 5 any value can come, at any time it can come. So that is the undetermined number of transitions, right? So that's why we cannot use the vector bins for the this non-consecutive and goto repetition. That will throw an error. Okay, so these are all the two types of errors we can see in the terminal when we use the vector bins. Okay, so for this the vector bins you can use. here in the for consecutive repetition we can use the vector bins. Here you can see, right? So but for non-consecutive and go to repetition you should use the scalar bins only. Okay, vector bin construct is not allowed. So now we will see the example for legal cover point transitions. In the last slide we have discussed all types of legal cover point transitions, right? So now we will see the example for all of them. So this is my cover group CG at POSIX clock. Here I'm at the positive edge of the clock. I'm sampling the variable data. Okay. So this is my sequence of sampled values for cover point variable data. These are all my inputs. The stimulus I'm generating. How many times I'm generating? So 5, 10, 15, 16, 17, 18. 18 times I'm generating the values. Okay, this is in this order. Just remember this is my input order for the variable data. So the first bin is for the data is 5 star 3. This is a consecutive operator, right? So 5 has to repeat for 3 times. That is in the consecutive order. That means in the while repeating the value 5 for 3 times, there should not be other value between the repetition. Okay. So this is my first input. From here to I have to check. Okay. So here 5 is there. So 5 has to repeat 3 times. 1, 2, 3. And there is no other value between the repetition. So here the bin B1 is covered for 1 time. Okay, after that the next value from here you have to count 1, 2, 3. So here also it is covered 2 times, and again from here 1, 2, 3. So again third time, and here 1, 2, 3. So total 4 times this B1 has covered for this bin. Okay, and this is how to see the coverage. Like I'm just showing the representation, it's not like that, but you will see 4 times the bin B1 has covered. Okay, and the next one is 1 after any value can come 3. Here this is the go to repetition operator. That means 3 can be repeated for 4 times, 3 can be repeated for 5 times, 3 can be repeated for 6 times. Okay, after that this I'm telling you go to repetition. Go to repetition means the next transition value should come immediately, right after the last occurrence of a value. So 1 followed by 4 to 6 go to non-consecutive 3s followed immediately by a 1. Immediately by a 1. Okay, so we will see. So here 1 is there. After 1, 3 can come at any time, and 3 has to repeat for 4, 5 or 6 times. So here 1 is there, and after that here 3 is there. So 3 is there. It has to repeat for 4 or 5 or 6. So 1, 2, 3, 4. 4 times it is repeated. Okay, so after 4 immediately 1 is there? No, but after that again 3 is there, right? So 3 can be repeated for 5 times also. So here 1, 2, 3, 4, 5. 5 times 3 is repeated. After immediately I'm getting the 1. So here it is covered, right? So here only one possibility is there. There is no other one to count from 3, right? So here B2 is covered for 1 time. So the next one is B3. Here 1 is there. After 1, 2 can come at any time, and 2 has to repeat for 3 or 4 or 5 or 6 times. There is a range, and this is a non-consecutive. And after that 5 is there. So this 5 doesn't have to come immediately. Okay, 5 can come at any time. This is a non-consecutive. So here 1 is there. After 1, 2 can come at any time, and 2 has to repeat at least for 3, 4, 5 or 6 times. So 1, 2, 3. 3 times 2 has repeated. After that anytime 5 can come, right? So here 5 is there. So this pin is covered here. And after that there is no 1 to count from the beginning, right? So this is one sequence. From here we have taken. So this is one sequence. And it has been covered for 1 time. And the next one is B4. Here I am using the go to repetition operator. 2 has to repeat for 3 or 4 or 5 times. Okay, in the non-consecutive order, and there is no other transition pins after this one. So it's like a non-consecutive only. Here 2 is there. 2 has to repeat for 3 times. 1, 2, 3. So here it is covered. B4 is covered, and I will count from here. 1, 2, 3. So here again covered, and this one 1, 2, no, only 2 times this B4 has covered. And B5, so 3 has to repeat for 3 or 4 or 5 times. Okay, 3 has to repeat for 3 or 4 or 5 times in the non-consecutive order. So here the first 3 is there. 3 has to repeat for 3 times, right? 1, 2, 3. So 1 time, and 1, 2, 3. Here 1 time, and 1, 2, 3 here. Okay, total 3 times I think. 1, 2, 3. 1, 2. Yes, only 3 times B5 has covered. Like this you have to check. So no need to check like this. Okay, everything we will get in the coverage report. I'm just showing you this for understanding purpose. To understand the concept, we have to know how transition bins will be covered in the coverage. So this is how they will take the transitions. Okay, and I hope you got the difference between consecutive, non-consecutive and go to repetition operator. And this is the example, same example I'll show you in the code also. Now we will see ignore bins and illegal bins. What is this ignore bins and illegal bins in coverage? By seeing the name only we can understand, right? Ignore and illegal. So these ignore bins are used to exclude the certain values or transitions from the coverage analysis, and illegal bins are used to make the values as illegal or to represent the invalid values, invalid scenarios. We can use the illegal bins. Okay, so these ignore bins and illegal bins are used to specify the conditions that we either don't want to cover or to represent the invalid scenarios. Okay, so we will see one by one. So the first one is ignore bins. Ignore bins are bins which are used to specify the values that should not be counted for the coverage. Okay, that means we can exclude the bins from being counted during the coverage. Ignore bins are bins which are used to specify the values that should not be counted for coverage. And these are basically the bins which are not important for the verification of the DUT and thus can be ignored. So if it is not important, we can ignore it, right? So to ignore the values or bins, we can use the ignore bins. Okay, and ignore bins are defined using the ignore bins keyword. So this is the keyword to represent the ignore bins. And the next one is illegal bins. So illegal bins are bins which are used to define the invalid bins. Okay, to represent the invalid values or invalid scenarios, we can use the illegal bins. And if the signal or variable takes this value, an error will be generated. And these are generally used to check the validity of the input or output signals and detect any invalid behavior. That means when you are using the illegal bins, when you declare the bins as illegal bins, and if the variable takes that value, then the runtime error we will get. So the error will be generated because these are used to check the validity of the input or output signals, and it will detect the invalid behavior of the DUT. Okay, for the occurrence of illegal values or transactions, a runtime error is reported. And illegal bins are defined using the illegal bins keyword. Okay, as I said, this ignore bins, illegal bins, these are all the keywords. So to represent the value as illegal or to represent the invalid scenario, we can use the illegal bins, and to exclude the bins from being counted during the coverage, we can use the ignore bins. So this is all about ignore bins and illegal bins. I'll show you the examples for ignore bins and illegal bins in the next video. Okay. Now we will see wildcard bins. And the wildcard bins definition causes all x, z or this operator to be treated as wildcards for 0 or 1. I think you are already familiar with the priority encoder. There also, when the MSB bit is significant and rest of the bits are don't care, that time we can use the x or z as wildcards for 0 or 1, right? Similarly here also. So these are mostly used when we are interested in some of the bits of the signal and rest can be don't care. That time we can use the x, z or this character to be treated as wildcards for 0 and 1. Okay, so if you see the example, you will understand better. Here I have an example. Wildcard bins b1 equals to 1, 1 and this operator. So this is treated as a wildcard for 0 and 1. Okay, and I'm using 1 bit as a wildcard. That's why 2 to the power 1 is 2. There are two possible combinations for this bin. Okay, 110, 111. Since I'm using the scalar bin, one bin will be generated. If I use the vector bins, I'll get two bins, right? For 110 is one bin and 111 is another bin. Total two bins will be generated if I use the vector bins. So here I have another example. Wildcard bins b2 equals to 1xz. Here I'm using 2 bits for wildcards. That's why 2 to the power 2 is 4. Total 4 combinations are available. Okay, 100, 101, 110, 111. Because x and z are wildcards for 0 or 1. It can be 0 or 1, right? So there are total 4 combinations. Since I'm using the scalar bin, only one bin will be generated. If I use the vector bins, then 4 bins will be generated. Okay, so wildcard bins are used to represent the bins with the wildcard characters. Okay, so here x, z and these operators are wildcards for 0 or 1. And if you see here for the variable data, I'm interested in the first bit of the variable. Okay, I'm interested in only the first bit of the data variable, and the rest can be any value. Okay, that time I can represent the bin as 1xz because the rest of the bits are don't care for me. It can be 0 or 1, but I am interested in the first bit of the data variable. That time I can represent the bins as wildcard bins by using the wildcard entries. Okay, so this is the example for wildcard bins, and I will show you in the code also how to write the wildcard bins and how to observe the bins. Okay, thank you.